There we go. Okay. And then I'm going to switch from this to my presentation slides.
So how long are you targeting your presentation for?
It'll be like 25 minutes.
Okay, that's good.
Again, it turns out that they don't always care as much as we thought they did about 20-minute timelines. That's good. Okay, so today I'm gonna get started. My presentation is on the design and evaluation of soft robotic hand orthoses that were designed with people with severe hand impairment after stroke. I'm Aaron Yerkowicz, and this is in partial completion of my Institute of Biomedical and Biomaterials Engineering PhD program. Thanks for being here today. I appreciate that. And then to anyone online, hi, thanks for being here too. Okay, so I'm gonna first go through the target population that I'm targeting with my devices, and then the thesis objectives, the methods, and then the results that came from those methods, and then the contributions of this project. So we know that after stroke, in the first month, people get larger amounts of care. They get 3 hours per day of therapy, whether that's speech, language, motor impairment, upper extremity or lower extremity therapy. And then after that first month, people are discharged, they go home, and they get just about 1 hour of therapy per week in a clinic. So it's just this huge decrease in the amount of therapy. And then after those first 3 to 6 months, people get even less. Usually nothing is covered for them. So as a result, they get limited access to rehabilitation and assistive technologies. Why this is such an issue is that we know that after stroke, people can still recover after those first 6 months. And second, they don't have the access to really regain those functions. And actually, third, we know that people usually have a lot of residual challenges in daily life that come from not having those rehabilitation recovery programs. So, for instance, a third of people do not regain the hand function required to perform their daily living tasks. The average person has 5 unmet occupational needs, and then also 83% have a lower quality of life than before their stroke. So for my focus of my project, I've really focused on people with severe hand impairment. And I'm just going to show you some videos of the types of people we're dealing with or working towards helping. So here, this is somebody whose hand is clenched. So this means that the muscles in their forearm are really tight, shrinking tendons that keep their hand locked in a certain position. And you can see just something that's as simple as opening up a water bottle becomes challenging. So like, you can also see it's hard to get the thumb around in order to really grip it and stabilize the object. This is the other type of severe hand impairment that I'm working with. So people who really can't activate those muscles to grip even a simple block, which you can think of not being able to grip your fork to cut your food, not being able to write with a pen. At the start of my project, what I was really interested in investigating were these passive dynamic splints, or orthoses. So devices you can wear on your hand, they have elastics on the back, and those keep your hand in more extended position. And what I found was that for people with less severe impairment, so people who could keep their hand relaxed and then also had strong grip force, they could keep their hand relaxed, so then the elastics would nicely extend their hand, and then they had enough grip strength that they could fight those elastics in order to grip an object. Whereas for people who had more tight hands, those elastics wouldn't extend the hand enough, and then they also wouldn't, for people who had weaker hands, they wouldn't be able to overcome the strength of those elastics to grip an object. I'll click the arrow button to move to the next slide. There we go. That always happens. Who had more clenched hands or had really weak hands, providing them enough force to do extension or enough force to grip an object really securely. So I worked on adding motors to these systems, as some groups have done in the past. And those motors provide extra force for the extension and then also extra force for gripping. The challenge that with the devices that are currently on the market are oftentimes you have to sit in a chair to use these devices because they're so heavy, and they're always wired to some external desktop computer or some unit. And then the second is that they're not affordable. All these devices are $20, $30, $40, $100,000, and these are just not devices that most clinics want to buy or would be something that somebody in their daily life would want to be able to buy to take home. And then third, they're very difficult to use. You need a computer screen to prompt you along through every single exercise, as well as a therapist there to set you up every single time you want to use these devices. So these were some of the challenges that I wanted to address in my project related to these active dynamic splints. So the inspiration I took was from some very industrious user-centered design processes I've seen in the past. So as an example here, just using a little pressure ball, you could progress the pages when you're reading. So you get some grip strength back as you were just doing a daily task you normally do. Here, enlarging the size of chess pieces using 3D printing, daily kitchen task tracking systems, and lastly, even just cutting holes in a paper box and then using that to grasp balls, put them into the box, and then playing with your kid and having this something that you could do your rehab without even thinking about it. The other inspiration I got was from some projects where they started with sketches, where they would sketch a device, show people after a stroke or spinal cord injury what they were thinking of, and then they would give feedback back in order to make a full product. And then from there, you go into 3D printing devices, you try putting them on, and then you can get more feedback from a tangible project. And then lastly, you can refine it to make something that looks nice and people will wear more often. So these are all examples of this user-centered design process where you have all your stakeholders engaged throughout the design process to provide feedback on what their needs are and to provide specifications for your device design, and then also to evaluate your process and then iterate through it again and again, making better products each time. So now I'm going to go through basically 3 text-heavy sections just so we can slide through and then get straight to the device we developed. So the thesis goal for this project was to design a usable and accessible robotic hand orthosis with occupational therapists and people after stroke, using this user-centered design process. The objectives, the first was to create these devices and then iterate their design over time with feedback from occupational therapists and people after stroke. The second was to determine how well people with severe hand impairments could perform hand function tasks, so opening your hand and closing your hand and then gripping tightly. And then extending on this, looking at how they could perform functional tasks, so something like reaching for a water bottle, opening the lid, or writing with a pen. So now the next one was a little bit more technical. It was going towards how accurately people could control these devices. So using buttons or their arm motion, different inputs, seeing which ones provide a really accurate control for extension and grip force. The fifth was to really get users involved in the process and really get their verbal feedback and rank their feedback on these Likert scales where you could see what's the most important to them and design devices to reach their satisfaction. And then lastly, to rate the overall usability of the system and ask really pointed questions about how likely they would be to use these devices at home and in the clinic. So then for the methods for this project, were to create, the first was to create these design specifications, first using literature, and then adapt them based on therapists and stroke survivors or people after stroke, their needs and their feedback throughout the process. The second was to design and manufacture these devices and then test them on our own to make sure they met those specifications. The third was to modify these devices as we showed them to therapists, had them demo these devices at our biweekly meetings, and then use those to iterate the specifications. And then finally, bring these robots directly to people after stroke have them test out the devices, give us more feedback, iterate the design specifications. So just quickly, the inclusion criteria. So it's people after stroke who couldn't grip and then extend their hands. So oftentimes they would grip and then they couldn't extend their hands fully, or they just didn't have the grip to begin with. So now the first devices I created were devices that provided 3-finger extensions. So you ask, why 3 fingers? This was because we wanted to minimize how complex the devices were, and we asked our therapists, and they said, these are the most important 3 fingers for doing daily tasks, because with your index, your middle, and your thumb, you can both do mostly like a cylindrical grasp, gripping these big objects, as well as you could do something smaller like grip a pen and be able to write your name. So that's why I targeted that initially. The design of the device, completely untethered, just you put it on and it starts working. It was an affordable system, and really the goal here is to reduce the number of motors, because their motors and the controllers are really what add up the cost of a device, at least from the manufacturing cost of the device. And then next, the system here, I have it right here. We added this design where it's like an open palm, so that it makes it easy to put in each finger individually, as opposed to if somebody has a clenched hand, it makes it hard to device. So you would just reach for the object, and when you wait, then it would grip the object for you. So now I'll go through the assessments and then show a video to really explain, or to show how this all worked in practice. The assessments for this system, we measured people's joint angles of their fingers. So this was to measure how much extension they could get and how much grip they could get with the robot and without it. Then we looked at the box and block test, which is kind of the minimum, or a low floor effects test. So this is for people who are we're just trying to see any improvement. This was a good test for that. It's also a test that other robots had done, so it's just a good way to validate how our system worked. And then lastly, we extended this to daily tasks, things like grabbing a water bottle and opening the lid. So the results from this, we were able to extend people's fingers partially. We were able to improve their range of motion, but we really didn't provide any grip strength. We thought the system might, but it didn't in actual practice. And then the results from this, people could perform these tasks better than they could before. So the box and block test, people could now grip blocks and bring them to the other side of the table, basically. And then second, for this water bottle grasp, if their hands were really tight, the system could open their hands up enough that you could put a water bottle in. And then if people currently could open up their hands but still needed assistance to put the water bottle in, then with the device, they no longer need that assistance, and they could just grip, pick it up, and do the task. So here is somebody who didn't have the grip strength. You can also see a lot of tone in their MCP joints, keeping really flexed. And then second here with the glove, positioning the arm, and then when you stop moving, you can see the actuator coming in, and then you're able to grip this object. Now, show it again just so that you can kind of get the point of this motion controller. So when you move and you grip, or when you move and stop, it grips, and then you move and then you stop again, then you can see it extending to help you grip. Here, the water bottle grasp. So see the hands are really tight. It's very hard to put the water bottle in. And then here you put the water bottle in, you could tighten the cap. And then with my assistance for operating the robot, you could then release the object. So now here's some weaknesses of the system. So we weren't really able to grip the water bottle strong enough, and as a result, it would just kind of slip out of your hand because we weren't really providing that much grip strength. So you can see she tries to put the cap back on and just slips out. So there were still some challenges to the system. One was in operating it using that arm motion controller. providing the grip strength to do these daily tasks. And those are things that we targeted with the next system. The other feedback we always got was, why are you extending just 3 fingers? Although it was important to our therapist to keep it very simple, the driving force from our stroke participants were that, why don't you extend all my fingers? I want to see them all extend. So that's what we did with the next system. Here, in order to provide both that finger extension and grip assistance with only one motor, I expanded it to this mechanical linkage system here. You can see the device here. Actually, when you pull it, it goes out, and then when you push it, then it would go back in. It's easier when I turn the motor on. And then also provided wrist support so that your hand didn't always turn in all the time. And then we used these Lego components that you could put on one component at a time. So if somebody's hand was clenched, you could just put on the finger part, and then you could put on the thumb part, and then you slide the wrist part on. So with this cool innovation, the other thing was this is voice controlled, so you could just say open and close, and it would just open and close. So this was actually a very interesting product in that we thought it was going to work really well, and then in practice, it wasn't as exciting as we expected. So we found similar finger extension and range of motion. The problem with testing grip strength, which is really the point of this system, was to increase grip strength, was that all these rigid components would really push on your skin and make it very hard or very difficult to wear for a long period of time. So we weren't actually able to test that. Also, since the system was formed to your fingers as opposed to being deformable, soft, something that would deform to the object, it was very hard to do things like grasp small objects like a pen or a block. So as a result, people couldn't do that test. And then people did similarly on grasping a water bottle because their hand shape was similar to the shape of the water bottle. Not going to show a video for that one. We'll just go on to the next one. So the next system here, still doing this 5-finger extension design, went towards 3-finger flexion. And the reason for that was then you could open up the device fully, and then it would be able to be easier to slide in each finger. So this is for the right hand. You just slide in each finger like that. And then also, like, the goal of this system was to make it kind of a soft version of that last system. So that's why we used a soft glove and then kind of a softer wrist brace on the other side. What was very interesting with this study was that we found that just by placing the motors onto the wrist brace instead of onto the soft glove part, we're able to extend people's fingers much more, which really made them a lot more satisfied than extending their fingers like this, because you're extending their fingers all the way. Also, we increased grip strength. What was interesting is that for people who didn't have grip strength, the system helped with their grip strength. But for people who already had grip strength, it wasn't as strong as the grip strength they had on their own. So just like a motivation for the future was to provide more grip strength, but we're able to provide some grip strength. The water bottle task, people were able to do a lot better because even if their hands were initially tight, they could extend fully and grip an object. And then we also added through in a couple more assessments, such as grabbing a fork, because it would be something like grabbing a fork and cutting food. And then second, we threw in this Quest satisfaction usability questionnaire, where people rank all these different components of the device, such as how big it is, how heavy it is, and how effective it was, and how easy to use it was, using a 5-point scale. What was interesting with this satisfaction scale is that we found like a huge disparity between people. So some people were on the side of like a 2, not very satisfied with the device. It was still hard for them to put on. It didn't provide really secure grip strength. And then it was very hard to control using their arm motion. But then on the other side, people were quite satisfied with the device, ranking it more in the 4 region, 5 region. this was because they were able to, it was able to extend their hand and really show them that their hand could move again. So those three challenges that I talked about before were things that I really wanted to address with the final version here. So different things that we added. First of all, added 5-finger flexion. So with the final system here, we have tendons that go through each of the fingers so that you'd have more grip strength to be applying force through all your fingers. We also added tendons that matched your thumb adduction, because what was interesting was before we were providing your fingers to move to this position, but it's really the thumb adduction that gets the force to actually grip those objects. So it was just kind of an interesting, huge change in grip force that just came from playing around with the technology, building many versions of this system. And then, interestingly enough, every time we kind of replicated the human anatomy more and more and more, the system started to work better and better and better. So, and then lastly with this system, we use this armband that you can just slide on your arm, and then it measures your muscle activity. And then it used an automatic controller in order to calibrate the system and then detect your gripping. So when you try to grip, then the system would assist your grip. And then when you relax, then the system would extend so that you could get release the object. So here I branched off and did a different set of assessments. So for this system, a lot of the reviews that I was getting back were, we want to use clinical assessments. We want something that we can interpret based on occupational therapy and practice, even something that we can compare how well these assistive improvements compare to rehab improvements. So we use the Spiegel-Meyer hand assessment, the Shadok arm and hand inventory, which is like 13 daily tasks that we just commonly do. I'll show a video of them later. And then we did this Quest usability scale again, as well as 2 more that were directly related to usability and your desire to use the system. Things that we found, we got clinically meaningful important differences in the Spiegel-Meyer and Shadok hand and arm inventory, which are much higher improvements than we would almost ever see with people just through rehab alone. And then the second was that people's Quest scores were higher, because even some people who did not see too much value in the device just as an assisted device, expected this system would be more valuable as a rehab device. So we started to get more people that were not very satisfied to be quite satisfied with the device. Although we still had some people who weren't very satisfied with the device because they found other ways to adapt. There's a lot of ways you can use your phone, go about your daily life using just one hand. And then so then our usability scores, we found the scores that suggest the system would be accepted in people's daily lives. And then in the desire to use scores, we had a lot of 7s. So like out of 7, people rated like that they were fully willing to use this device in the clinic, at home, in their daily life. And then these scores were somewhat weighted downward because there were a couple of people who still thought this was not really something that's useful for me. Maybe it's too hard to put on. So then their scores of 1 would really bring the scores down for this. So now I'll show a video of how the system operated. Soft wearable robots are advancing and merging the fields of rehabilitation and assistive technology to help millions of people recover hand function after stroke. And then squeeze as much as you can. So this is somebody who has no motion in his hand. But what was interesting is we could still see muscle activity and use that to grip and extend hands. It provides 5-finger grip assistance when the user attempts to grasp, and 5-finger extension assistance relaxes when the user relaxes the shoulder, elbow, wrist, and hand. 9 people with severe hand impairment after stroke completed a hand function assessment and 13 daily living tasks, like holding a phone or toothbrush, doing up a zipper, and cutting food. With my hero, All 9 participants surpassed clinically meaningful important differences on the hand function assessment, and 4 surpassed these differences on the daily living test. 9 participants incorporated their affected hand into more of these daily living tasks and performed them more independently.
Like that. Yeah, I've never been able to do this.
Majority of participants were satisfied with My Hero and found it to be useful and easy to use.
So this was an interesting
Some
one
participants desired to use My Hero in the
because
clinic and
it was
at
getting
home
closer to
during
winter and people were starting to think, oh, soon I'm
Our
going to have to put
developments
my
and
coat
findings
on,
provide
which is
therapists
things
and
that
people
we
with
normally don't
exciting opportunities for
think are going to be
integrating
very important.
bioelectric soft robotic gloves into their rehabilitation programs and daily routines. This will enable their independence and motivate greater use of the affected upper extremity to enhance recovery. Check out our paper and data set of forearm electromyography, acceleration, and orientation recordings collected during these hand function and daily living task assessments.
So I hope you enjoyed the video. So now I'm going to go through the thesis objectives and then the summary of the results. So first of all, something that was very interesting about this work is that I was able to go through this iteration cycle 4 times throughout my project, which is usually you only have the time to go through once. But bringing the engineering in with occupational therapy, set in such a close-knit group, we're able to get through a lot of these iterations. We found performance enhancements both in hand function and in people's ability to do these daily living tasks more independently. We found robot control accuracies very close to 100% for the button control, the hand motion, as well as using their muscle activity. But then with the voice control, it was still very hard for people to control just because our Google Assistant wasn't able to detect people's voice. You can think every time you try to text somebody, it might spell one word wrong. And in that case, it was similar to with the glove. You'd say open, it wouldn't open. You'd say close, it wouldn't close, and you have to say it a couple more times. Also, people with different speech impairments, it was also kind of very tough for them. So next was user satisfaction. We found that a large portion of people were quite satisfied with the device, but then there were still some people that we could meet their needs better, both with other assistive devices as well as making the glove easier to put on and set up. And then similarly, our user satisfaction scores are very similar to our usability scores, where we had this large portion of people who liked it as an assistive device or as a rehabilitation device or both, and would like to use the device in the clinic and at home. So those are things that we're exploring now. So lastly, in summary, a useful and accessible device has been developed. Our design documents are now online, open source for anybody to build. The robot enabled stroke survivors to perform activities of daily living more independently. We have design specifications, novel mechanisms and control schemes that have been created, as well as we now finally have assistive data on hand exoskeletons and how well they can help people do hand function in daily tasks. And then lastly, the project achievements will hopefully motivate more people to take this transdisciplinary design process, really integrating a whole team with different stakeholders throughout the design. So with that, I'd like to thank all of you, one, for being here today and for all your motivation and support and thoughts that have really, you can probably see how your thoughts have infused into this project. And then to Alex, I wish he was here today, but I'm sure he's looking on and happy. And then I'd like to thank our people after stroke who have participated through a lot of these studies, as well as healthy participants, some in this room, and then our clinicians like Debbie, you might know, Debbie Huber, you might know, all the interns that have been part of this project, and then a lot of therapists, both here at Toronto Rehab as well as in other clinics throughout the GTA, in Manitoba, now in the US and India as well. So with that, I guess that's actually the last slide, so thank you for all being here today. And thanks to everybody who is online. Send me some comments in the link below. So now I'm just clicking end stream, and it's not ending.